Okay, we've looked at a power plant and we've defined the thermal efficiency of a power plant. System operating a cycle making net power. Now we've got refrigerators and heat pumps, but refrigerator in particular, I want to show you how engineers characterize the performance. How well does a refrigerator perform? So this video is called, so we're in chapter 5, second law of thermodynamics. We're looking at things that are possible and impossible. We're going to be looking at what's the best you could possibly do. So we're trying to characterize the performance of systems operating in a cycle. And in this video, I'm going to show you how to characterize the performance of a refrigerator. And we call that coefficient of performance. And in engineering jargon, that's COP, coefficient of performance. Okay, so you've got a refrigerator. You've got one. Let's go through that same drill that we went through with the power plant. You were the power plant manager. Well, now you're the owner of your refrigerator. What's your main objective of owning a refrigerator? What's that main objective? And is there any expense involved in running that refrigerator, or is it just sort of appears in your kitchen and it runs on its own? Well, you know what the answer is. If you pay your own bills, you know what the answer is. Your main objective is to keep your food and beverages cold or cool. Okay. And it does take money to keep your refrigerator running. And that's in terms of your electric bill. And it can be substantial from time to time. So yeah, the electric bill, the cost of electric power to run your refrigerator, that costs you, doesn't it? Okay. So let's do then that same word, the word trick that we pulled for the power plant. Wouldn't you say that your main objective is the energy sought? So removing heat from your food and beverages, that's what you're seeking to do. That's your objective. That's the energy sought. And how about the energy that costs? Well, that's almost like a no-brainer, isn't it? The energy it costs is your electric bill. What you have to pay in terms of electric power, electric energy, to operate your refrigerator. Energy sought and energy that costs. Let's do our basic schematic and label energy sought and energy that costs on our schematic. And so I've tried to add something to TH and something to TL to get in your mind what's this all about, rather than just memorizing a sketch that you have to draw. Your high temperature reservoir, well, let's go down to the low temperature reservoir first, because that's where the energy sought is, correct? I've labeled Q.L as the energy sought. This is it's a tiny little clip, but it's Ben and Jerry's ice cream. This is the cold space, like your refrigerator. That's the low temperature reservoir, and you're seeking to keep your Ben and Jerry's frozen. Energy sought, Q.L. Okay, let's go up to the high temperature reservoir. Well, that's the surroundings. That's your kitchen. So I've drawn a little stick figure of you standing in your kitchen to try to visualize what the schematic is all about. All right, and then I've labeled energy that costs. Well, that's the power that it costs to run your refrigerator. And I've written down the first law, of course, over on the right. Q.H minus Q.L equals W.net. Hope that's coming pretty naturally to you now. Okay, refrigerator's running steadily, so I've got those dots over top of it. Now this is the way we're going to define the way we engineers define the performance of a refrigerator, and we call it coefficient of performance, beta. This is Greek letter beta. This is not B. So beta sub ref, that's for refrigerator. Beta refrigerator is the energy sought over the energy that costs. It's those same words as the power plant. So remember those words. Energy sought over the energy that costs. I owe so much to my professors in thermo that taught me this little trick, because now if I've got my schematic in front of me, which I've got it over here, here it is, okay, I can immediately plop down the formula, okay? Energy sought, Q.L. Energy that cost me, W.net. So I write it down on my paper, and then I can write down my first law. So beta refrigerator, Q.L over W.net. energy sought for energy it costs, equals Q dot L, same numerator, divided by, denominator is going to be Q dot H minus Q dot L. That's a statement of the first law for the denominator. And then, of course, the same drill for a piston and cylinder executing one single cycle. So over here on the right, your units are kilojoules divided by kilojoules. And over here on the left, which is most common, you've got kilowatts of heat removal from the cold space divided by W dot net, the power in kilowatts that cost you. And so the units, beta, coefficient of performance, is going to be dimensionless. Oh, and my red, notice here, also called COP refrigerator. This is a common, it's common in manufacturing information at Lowe's and Home Depot. You don't see Greek letter beta, but you do see COP, coefficient of performance. Let's do a numerical example. And let the questions be, how much power is it going to take to run this refrigerator, and what's the coefficient of performance beta? And just to as a cheat sheet, I've written down the first law and the expression for coefficient of performance. But you don't need those formulas, because with the schematic, I'm given Q dot H is 12 units and Q dot L is 9 units. Well, what do I have to? I've got to make something up with power, don't I? Well, I've got to put out 12 up here, the high temperature reservoir. I'm putting in 9 here with my eyes. I've got 3. So I've got 3 units of power going in. So what is the coefficient of performance? Energy sought, 9 divided by the energy it costs, 3. 9 over 3 is 3. The coefficient of performance for this example is going to be 3. Let's see how we did. We did great. W dot net, 3 units. That's like falling off a log. Now, for coefficient of performance, all you got to do is know that definition. Energy sought over the energy that costs 9 over 3, and you've got it. Or if you want to go the formula route, let's see. It's Q dot L divided by the quantity Q dot H minus Q dot L, 12 minus 9. That's 3. So, and what did you just observe? When an engineer characterizes the performance of a refrigerator, the COP, the coefficient of performance, is a value greater than 1. It's not a percentage. And so a lot of students get all worried and nervous. Oh, I've got a beta of 3. It's not a percentage. That's okay. It's the definition. And so coefficient of performance for a refrigerator, it's a value greater than 1. It's a ratio. Energy sought over the energy that costs. And in this case, the energy sought is a bigger number than what it costs you to run it. It can still be expensive to run a refrigerator, don't get me wrong, but you're transferring a good bit of heat with a small amount of work input. Pretty cool. Here's some other examples of systems that operate on the refrigeration cycle schematic. The window air conditioning unit, it works on the refrigeration cycle, identical. Okay. And this would be an HVAC unit is simply a large version of a window air conditioner. Okay. Same idea. Okay. Is the refrigeration cycle is working for your whole house air conditioning system. And down here, I've kind of depicted the compressor condenser section of a heat pump. And some of you may live in residences, whether it's an apartment or a home, that uses a heat pump as the source of heating in the wintertime. So that also operates on the refrigeration cycle. So very common systems operating in a cycle, all of which are the basic refrigeration cycle. And now you know how to quantify the performance for air conditioning systems and refrigerators. We'll get to heat pumps a little later. Okay, and so there we go, where we can recap. We define the refrigerator coefficient of performance, Greek letter beta, beta refrigerator, also called COP. And we can remember this. So we minimize the things that we have to memorize. We just know this performance measure for a refrigerator, beta, is the energy sought over the energy that costs. As long as we can draw our refrigerator schematic, almost like automatic, we can figure out the rest. And so that's a key, is learning how to figure out the rest rather than depending on a formula sheet and lots of formulas and special cases and things like that. Okay, I hope you're seeing how things are falling into place. Now we've gotten two major pieces of equipment that's operating in a cycle. We've got a power plant, also heat engine, or a refrigerator, and we now know how to quantify the performance of each of those pieces of equipment. Stay tuned for heat pump.